Hey there, ever stop to think, what exactly is space? Or time? Seems obvious, right? Seconds tick, meters stretch. But here's the twist. Space and time, they are far stranger than we ever imagined. They bend, they stretch, they ripple. Sometimes they even loop back on themselves. From black holes to the Big Bang, from tiny electrons to entire galaxies, everything in the universe plays on this mysterious stage. And the deeper we dig, the less real it seems. What if space and time aren't what you think they are? What if they're just emergent, relational, maybe even illusions? Stick around. By the end, your mind will never see reality the same way again. Don't forget to subscribe. This journey is just beginning. Drop where are you right now, or what country, and how old are you, and we will begin our journey through space together. Think you understand space and time? Think again. Every day, you move through space like it's a simple stage. You open doors, drive cars, and walk down streets. You assume time ticks the same everywhere. 1 second here, 1 second there. Life feels uniform, predictable. But the universe laughs at our intuition. Out there, on cosmic scales, space isn't fixed. It stretches, bends, and curves. Gravity doesn't just pull, it warps space and time itself. Imagine a trampoline with a bowling ball in the center. Step closer, and you fall toward it. That's gravity, not just a force, but geometry. Time? Not so simple. The closer you are to a massive object, the slower time ticks. Your clock on Earth runs faster than one near a black hole. Move fast enough, like near the speed of light, and your second stretches. Hours for you could be centuries for someone left behind. Time is not absolute, not universal. Your intuition fails because our daily life moves too slowly to notice. And space isn't what it seems either. Galaxies aren't just drifting through space, they're carried apart by the expansion of space itself. Some galaxies recede faster than light, but they're not breaking the cosmic speed limit. They're standing still, and the space between them is stretching. It's a cosmic illusion. Your senses can't detect it, but math reveals it. Even energy, the stuff that powers your coffee maker, misbehaves. In an expanding universe, energy isn't always conserved. Photons stretch, losing energy as space grows. Your everyday rules crumble when scaled up to the cosmos. And the weirdness doesn't stop there. At the tiniest scales, space and time might be granular, made of tiny, indivisible pixels of reality. Imagine walking across a beach. Up close, it's sand, tiny grains. Step back, and it feels smooth. That's what space and time might be like at the Planck scale. So, your everyday intuition? Misleading. Your second, your meter, your straight line, they are local illusions, not universal truths. But don't get discouraged. Understanding these cosmic realities is the first step to mastering them. From Einstein bending time to quantum grains of space-time, the universe doesn't play by our simple rules. And once you see it, life itself feels a little more magical. Stay with me. Next, we dive deeper: entropy, heat, and the demon that tried to cheat the universe. Reality is stranger than fiction, and your journey has just begun. Before Einstein, before relativity, there was Newton. And Newton had a simple, elegant picture of the universe. Space, infinite, flat, absolute. A stage, fixed, immutable. Time, uniform, flowing steadily. 1 second here equals 1 second anywhere. The universe was a clockwork machine, predictable, neat, elegant. Newton imagined planets orbiting like gears, apples falling straight to the ground. No curves, no bends in the stage itself. Space didn't care who you were or where you stood. Time didn't care how fast you moved. In Newton's world, objects moved through this fixed stage. Gravity? a force acting at a distance, pulling objects toward one another. But the stage itself remained untouched, a cosmic backdrop, unchanging and eternal. It worked really well. For centuries, Newton's mechanics predicted the motions of planets, moons, and comets with stunning accuracy. Engineers, astronomers, and even navigators relied on it. Ships crossed oceans, satellites orbited Earth, all thanks to Newton's simple absolute framework. But the simplicity hid a problem. What happens when objects move faster, or near massive bodies like the Sun? Newton didn't know. His equations assumed the stage never bends, never stretches. They assumed instant action at a distance. Gravity pulled, and the universe obeyed immediately. No delays, no distortions, and that's where the cracks appeared. By the late 19th century, scientists saw strange phenomena. Mercury's orbit wasn't exactly as predicted. Light bent near massive objects, a mystery for Newtonian mechanics. The stage, once assumed rigid, couldn't account for these quirks. Still, Newton's picture is powerful. It shapes our intuition even today. You throw a ball, it arcs, it lands, perfectly predictable. Your phone, your car, your spacecraft, they all operate on this local approximation of absolute space and time. Newton is the everyday stage we live on, even if the cosmic stage is far stranger. The genius of Newton? He gave us a framework that works for daily life. He made the universe understandable, and for hundreds of years, it was the truth. But the universe doesn't care about convenience. It's more flexible, more elastic, more chaotic than Newton imagined. Einstein would soon show that the stage itself can bend, twist, and ripple. Time isn't uniform. Space isn't rigid. Newton's absolutes were only the first act. Stay tuned. Next, we explore Maxwell's demon, entropy, and how the universe teaches us that even the simplest notions of time and order are not as they seem. Newton gave us a fixed stage, but the universe had secrets Newton never imagined. Enter thermodynamics, the science of heat, energy, and the strange rules that govern them. It all begins with the idea that energy cannot be created or destroyed, only transformed. Simple, right? Yet this led to a puzzle. Entropy, a measure of disorder. Left to itself, systems become more disordered. Hot coffee cools down. Ice melts. Gas spreads evenly. The universe has a natural direction. A one-way street. The arrow of time. James Clerk Maxwell added a twist. Maxwell's demon, a tiny imaginary creature controlling atoms, sorting fast ones from slow ones. Could it reverse entropy? Could it defy the arrow of time? For over a century, scientists argued. Some said the demon must expend energy, so entropy still rises. Others realized it's about information. Knowing the speed of atoms is key. Processing information produces heat. Forgetting information produces even more. Landauer's principle shows that erasing one bit of information releases a tiny, unavoidable amount of energy. Entropy isn't just a curiosity. It's the reason time feels like it flows. Without entropy, the past, present, and future would blur. Time might even lose meaning if the universe reached maximum entropy. Think bigger. The arrow of time isn't just coffee or ice. It's cosmic. Stars burn, planets form, galaxies evolve, all because energy flows from low to high entropy. The universe began in a low entropy state, incredibly smooth and ordered. Gravity then clumped matter, creating stars, planets, and life. Entropy increases as the universe ages, giving time its direction. Thermodynamics is also linked to computation. Every calculation, every bit processed, contributes to entropy. Our digital lives mirror cosmic laws. Even in a supercomputer, forgetting information releases heat. The arrow of time emerges from the microscopic actions of countless particles. Here's the mind bender. The laws that govern individual atoms don't care about time's direction. Electrons repel, neutrons decay, they behave the same forwards or backwards. Yet the macroscopic world clearly moves forward. Entropy is the bridge. It's the microscopic chaos that creates our experience of a flowing present. Thermodynamics taught us time isn't just a human construct. It's woven into the universe through energy, disorder, and information. From cooling coffee to the fate of galaxies, entropy defines what past and future even mean. Newton's stage was fixed. Maxwell and thermodynamics revealed that the stage itself is dynamic. Time has a direction. Space and matter evolve. The universe is no longer a simple clockwork, it's a story unfolding. Entropy rules. Disorder grows. Time moves forward. Then comes a thought experiment. James Clerk Maxwell, a Scottish genius. He asks, what if we could cheat entropy? Meet Maxwell's demon. Tiny, invisible, omniscient. It watches every atom. Slow atoms to one side, fast atoms to the other. The result? A hot side and a cold side. Order from chaos, defying the second law of thermodynamics. But hold on, the demon isn't magic. It needs information. It must know each atom's speed. It must act on that knowledge. Processing information costs energy. Even a thought experiment has limits. Erasing data produces heat. Landauer's principle shows it. Every forgotten bit releases energy. The universe won't be cheated. Entropy still rises. Order requires effort. Information links energy and disorder. This was a revelation, not just about gas or heat. It was about the fabric of reality. Chaos and order are tied to knowledge. Think about your computer. You type, you delete. Every deletion produces heat. Even in tiny amounts, the law applies. The arrow of time marches on. Maxwell's demon also changes our view of time. Time isn't just a passive backdrop. It's active. Information and energy shape its flow. Chaos isn't random, it has rules. Order isn't free, it demands work. Time emerges from this struggle. Maxwell's demon was more than a thought experiment. It bridged classical physics and information theory. It hinted at the quantum world to come. It hinted that reality is deeper than what we see. The lesson is clear. The universe is governed by rules you can't ignore. Energy, information, and entropy are inseparable. Time's arrow exists because forgetting, processing, and energy dissipation are unavoidable. Even the smallest action, like erasing a bit, ripples outward. Chaos spreads. Order is maintained only temporarily. Time is defined by these interactions. Without Maxwell's demon, we might not understand it. Maxwell gave physics a puzzle, a riddle linking atoms, energy, and information. A tiny demon reshaped how we think about time itself. So, next time you wonder why coffee cools or ice melts, remember Maxwell and his demon. They showed us that the arrow of time is real. It's in every particle, every atom, every bit of information. Entropy grows. Disorder spreads. Time moves forward. But why? Why is the past different from the future? The answer is forgetting. Not human memory, atomic memory. Information that vanishes. Think of adding two numbers. 3 plus 2 equals 5. Easy. But reverse it. What two numbers made 5? Impossible to know. That's the essence. Input is lost. Information erased. Energy is released. The Landauer limit proves it. Erasing one bit creates heat. At room temperature, it's tiny. 1/100th of an electron volt. But computers erase billions of bits every second. Heat is inevitable. Entropy rises. This is why time has direction, forward, not backward. Because the universe forgets as it goes. Each moment consumes information and energy. Macroscopic processes follow this rule. Coffee cools, ice melts, stars burn fuel. All irreversible. all consequences of information being lost. Microscopic physics is different. Electrons, quarks, photons, they don't care about time. Flip the clock backward. They behave the same. No arrow of time there. So, where does the arrow come from? From collective forgetting. Countless particles are losing information simultaneously. From entropy spreading across the universe. Even at cosmic scales, it matters. Stars form from collapsing gas clouds. Planets emerge. Life evolves. Energy converts. Information disappears. Time marches on. Without forgetting, the future would not exist. Every particle would be trapped in its past. No change. No growth. No history. Maxwell's demon hinted at the connection. Information can create order, but only if energy is spent. Erasing that information restores disorder. Time flows because the universe cannot hold on to everything. Consider black holes. Information falls in. Some is radiated away as Hawking radiation. Entropy increases. Forgetting defines cosmic evolution. Even our consciousness is tied to this principle. We remember, we forget. Each act of forgetting shapes our perception of time. The past exists in memory. The future emerges in forgetting. Entropy is subtle. It governs atoms, computers, planets, and stars. It defines why you age, why the universe evolves, why time seems real. So next time you delete a file, or watch ice melt, or feel a second pass, remember, time exists because forgetting exists. Entropy is the engine. Forgetting is the fuel, and the arrow of time is the path it carves through the cosmos. Everything in the universe computes. Even you, even the stars, even empty space, in a way. But what does computation cost? Energy, always. Rolf Landauer, 1961. A quiet genius with profound insight. Erasing one bit of information produces heat. Not optional, not negotiable, inevitable. Think of a computer. You type, click, scroll. Each logic gate processes input, and then forgets it. That's the key. Input goes in. Output comes out. But the original data? Gone. Lost to the universe. That's when heat is generated. Tiny amounts, yes. 1/100th of an electron volt at room temperature. Insignificant? Not for billions of bits. And certainly not for cosmic scales. Computers today? Thousands of times hotter than the Landauer limit. Inefficient. Wasteful. But by 2035, chips may approach it. Approach perfection. Why does this matter? Because it links information to physics. Information is not abstract. It has weight in energy and cost in entropy. Maxwell's demon reappears, sorting atoms with knowledge. But to act, it must erase. Each erased bit adds heat. Entropy increases. The demon cannot cheat the second law. Even your brain obeys this law. Neurons fire, memories stored, memories forgotten, tiny energy costs, tiny contributions to cosmic entropy. Landauer showed us a deeper truth. Time and computation are linked. Forgetting defines forward motion. Entropy grows as information vanishes. Quantum computers, they complicate the story. Superpositions store multiple bits. Entanglement allows parallel processing, yet the Landauer limit remains. Erasing information always costs. The universe itself is computing. Stars, black holes, atoms, and light. Processing information, losing information, generating heat, shaping the arrow of time. It's humbling. Even the most abstract thought, the tiniest calculation, it is rooted in physics. Everything is matter, energy, and information. So, next time you think of computers, think bigger, think universal. Every operation, every deletion, adds a whisper to the heat of the cosmos. Landauer's insight is simple, yet profound. Forget, and you create the future. Erase, and the universe ticks forward. Information, energy, and time are inseparable. And this sets the stage for understanding light, motion, and the cosmic speed limit. The universe computes, and the cost is inescapable. Time feels real. We wake, we live, we sleep, past, present, future. But why does it flow one way? Entropy, the key to the arrow of time. Disorder increases. Coffee cools. Eggs break. Stars burn. Maxwell's demon teased us. Chaos could be beaten. Order could be restored, but only at a cost. Landauer showed the truth. Forgetting is fundamental. Every erased bit of information increases entropy. Time moves forward because we forget. And this isn't just physics. It's a human experience. Your memories, fleeting as they are, mark the past. The things you cannot remember vanish, leaving room for new moments. Think about it. If you remembered everything perfectly, would the future even exist? Time would stall. No novelty, no growth. Entropy shapes life. It dictates decay and renewal. It drives evolution, thought, and civilization. Without it, we wouldn't age, we wouldn't learn, we wouldn't change. Even our minds obey the laws. Neurons fire, memories form, some fade. Forgetting isn't failure, it's essential. Entropy also links us to the cosmos. Stars burn fuel, creating order and chaos simultaneously. Galaxies form, collide, and disperse. Energy flows, information is lost. Time marches on. Your life is a microcosm of this process. Birth, growth, decay, moments remembered, moments forgotten. Each small act of forgetting pushes the arrow of time forward. Physics and philosophy merge. The universe is impartial. It does not care about human preference. Yet through our memory and perception, we experience the flow of time. Even love, loss, joy, grief, they're tied to entropy. We cherish memories. We mourn, forgetting. But each act of letting go keeps the universe moving. So when you feel time slipping, or wonder why the past feels fixed while the future looms unknown, remember, entropy is the answer. Not just an abstract concept. It is the cosmic engine behind every second. And here's the kicker. Time is emergent. It exists because entropy exists. The universe computes, forgets, and evolves. We are part of that computation. Every heartbeat, every thought, every decision, it is a small battle against disorder. Yet in losing, we create the future. The past solidifies. The future stretches endlessly ahead. Entropy, time, memory, life, all inseparable, all essential, and all pointing to one simple truth. We experience time because the universe forgets. Light is fast, faster than anything we could imagine. But how fast? For centuries, scientists wondered. Some thought it was infinite, others guessed, but no one really knew. In 1676, Ole Rømer had an idea. He watched Jupiter's moon Io. Every orbit, Io disappeared behind the planet. Timing these eclipses, Rømer noticed something strange. Predictions were off, sometimes early, sometimes late, and the pattern depended on Earth's distance from Jupiter. Rømer realized the solution. Light takes time to travel. It is not instant. It has speed. He estimated it at 211,000 kilometers per second. Not perfect, but revolutionary. Christian Huygens refined the measurement. By comparing timings, he brought it closer to today's 300,000 kilometers per second. The first clear proof that light was finite. This discovery shook the foundation of physics. If light had a speed, what was it relative to? Earth? Sun? Or some mysterious medium? The luminiferous ether was proposed. A cosmic jelly fills all space. Light travelled through it, like sound through air. But experiments failed to detect it. No ether wind, no absolute frame of rest. Just confusion. These questions simmered for centuries. Light's speed seemed constant, but constant relative to what? The answer would require a leap in thinking. Meanwhile, Maxwell's equations were quietly rewriting physics. Electricity and magnetism are intertwined, and light emerged naturally, a self-propagating wave of electric and magnetic fields. Its speed is embedded in the math. But the question of reference still lingered. These early experiments laid the foundation. They showed light was measurable, not infinite. They challenged assumptions about space and motion. They hinted at deeper truths about the universe. And they set the stage for Einstein, for relativity, for the realization that light's speed is absolute, not relative to Earth, Sun, or ether, absolute and unchanging. Think about it. Every time you switch on a flashlight, every signal sent across the universe, every observation of distant stars, light carries its message at the same speed. A cosmic speed limit, a clue to the fabric of reality, the beginning of a journey from the familiar to the unimaginable. Rømer, Huygens, Maxwell, they opened the door, and Einstein walked through it. The quest for the speed of light transformed our understanding of space and time forever. Light travels, but how fast? For centuries, this question haunted astronomers. Was it instant, or did it take time to reach us? In 1676, Danish astronomer Ole Rømer set out to find the answer. He focused on Jupiter's moon, Io. Io completed an orbit around Jupiter roughly every 42.5 hours. Rømer expected to predict exactly when it would disappear behind the planet. But something was off. The timings didn't match predictions. Sometimes, Io disappeared earlier than expected. Sometimes later. At first, Rømer wondered if his calculations were wrong. Then he noticed a pattern. The timing error changed depending on Earth's position relative to Jupiter. When Earth was moving away from Jupiter, Io's eclipses were delayed. When Earth was moving toward Jupiter, they occurred sooner. Rømer realized what was happening. Light takes time to travel across space. The further the distance, the longer the delay. I wasn't late. The light from Io was simply traveling at a finite speed. He made a bold estimate. About 211,000 kilometers per second. Not exact modern measurements show roughly 299,792 kilometers per second, but revolutionary for its time. For the first time, it had shown that light was measurable, and that it was not instantaneous. Rømer's discovery challenged centuries of thinking. If light has a finite speed, space and time are not as simple as they seemed. People had imagined light spreading instantly through an invisible medium. Some called it the luminiferous ether. Rømer's measurements suggested otherwise. Light's travel was a physical process. Christian Huygens, a contemporary of Rømer, refined these calculations. Using Rømer's data, he improved the speed estimate. This was still decades before modern instruments, but it laid the foundation for future discoveries. Rømer's work had consequences far beyond astronomy. It implied that space and time could be measured with precision. It hinted that there might be a cosmic speed limit, and it forced physicists to reconsider assumptions about motion and reference frames. Before Rømer, light was mysterious and elusive, instant, untouchable, assumed infinite. After Rømer, it became a tangible, measurable quantity. The door to relativity was opening. The story of light's speed is not just about numbers. It's about curiosity, observation, and daring to question what seems obvious. Rømer observed moons, noted small discrepancies, and saw a universal truth hidden in plain sight. Fast forward centuries, and this work directly influenced Einstein. If light has a finite, absolute speed, then space and time themselves must adapt. Measurements of distances and durations are relative. This is the seed of special relativity. Rømer may not have known he was rewriting physics, but by measuring light, he revealed that the universe is governed by fundamental limits. Limits that shape motion, causality, and reality itself. So, next time you look at a star, remember, its light traveled for years to reach you. Not instant, measured, finite, and thanks to Römer, now we know it's fast, but not infinite. Electricity, magnetism. For centuries, scientists studied them separately, but James Clerk Maxwell saw a connection. In the 1860 seconds, he began writing equations. 4 equations, simple-looking but profound. They described how electric and magnetic fields interact. Maxwell discovered something extraordinary. Changing electric fields create magnetic fields. Changing magnetic fields create electric fields. Fields could sustain each other. Self-propagating waves. What does this mean? These waves move through space at a fixed speed, a speed calculated from electric and magnetic constants, a speed identical to the speed of light. Maxwell realized light is an electromagnetic wave. Electricity and magnetism together create light. Visible light, infrared, ultraviolet, all the spectrum. This was a revolution. No longer was light mysterious. No more ether needed. It was waves of electric and magnetic fields, self-contained, traveling through space. His equations predicted more. Radio waves, microwaves, all forms of electromagnetic radiation. Science had a new tool to explore the universe. Maxwell also embedded the speed of light in his equations. A universal constant, no matter the source, no matter the observer. This was the first hint that space and time might be linked. Maxwell's work transformed physics. Electricity, magnetism, and optics became unified. One theory explained many phenomena. Practical inventions followed. Telegraphs, electric motors, radio. But there was more. If light has a fixed speed, what does that mean for moving observers? If you chase a light beam, what do you see? Classical mechanics could not answer. Newton's absolute space and time began to falter. Maxwell's wave theory also had aesthetic beauty. Symmetry, elegance, mathematical simplicity reveals deep truths. Many called it the crown jewel of 19th century physics. Scientists debated, could all forces be unified like this? Gravity was still separate. But Maxwell inspired future generations. Einstein, Lorentz, and others built on his vision. Light, speed, and fields were now intertwined, no longer just phenomena to measure. They became keys to understanding space and time. The universe had structure, order hidden in Maxwell's equations. Maxwell himself sensed the philosophical weight. He wrote about the universe in terms of fields, not particles alone, not empty space. Space is filled with invisible forces, a dynamic, interconnected fabric. So when you turn on a light, think of Maxwell, a Scottish physicist who saw electricity and magnetism as two sides of the same coin. Who showed that light is a wave of fields? Who laid the foundation for relativity? And who revealed that the universe speaks a mathematical language? Electromagnetism became a bridge between what we see and what we measure, between the physics of the lab and the physics of the stars. Maxwell unified forces. Light emerged. Space and time would never be the same. For centuries, scientists assumed light needed a medium. Sound travels through the air. Water waves travel through water. So, why not light? They called it ether. A mysterious, invisible substance fills all space. Silent, immovable, absolute. The ether was supposed to be the stage for light waves. It defined absolute rest. Everything moved relative to it. Experiments began. Michelson and Morley in 1887. The famous interferometer. They tried to measure Earth's motion through the ether. Light beams, split and recombined, should show tiny shifts. shifts caused by motion through the ether. But nothing happened. No shift, no effect. The ether was invisible, unmeasurable, perhaps non-existent. Physicists were puzzled. How could light travel without a medium? Waves need a stage, don't they? Some proposed adjustments. Lorentz and Fitzgerald suggested length contraction. Objects shrink in motion through the ether. A patch, not a solution. The deeper problem remained. This crisis revealed a bigger truth. Absolute space and time were illusions. If no absolute rest exists, then motion is relative. Not just position, not just speed. Everything is relative. Enter Einstein, 1905. Special relativity. He boldly dismissed the ether. Light doesn't need a medium. Its speed is constant. For all observers, this was radical. No absolute frame, no cosmic stage, only relative motion. The ether died quietly. What survived was the principle of relativity. All laws of physics are the same for all inertial observers, but the lesson was deeper. Nature doesn't obey our intuitions. Space is not a fixed backdrop. Time is not absolute. Both are part of the universe's dynamic fabric. Experiments after Einstein confirmed it. Light's speed remains constant, even on moving trains, even chasing it through space. The ether's demise cleared the path for relativity, for understanding space-time, for modern physics, yet it also left questions. If light doesn't need a medium, what is space? And if motion is relative, what is time? These questions drive physics today. From black holes to quantum mechanics, from the Big Bang to the edges of the universe, the ether was a dead end, but it taught scientists to question assumptions, to test everything, to let go of old ideas. Sometimes, to see the truth, you must abandon what seems obvious. Absolute space, absolute time, invisible ether, all illusions shattered, and a new era began. Relativity, space-time, the universe, stranger than we ever imagined. Newton's laws had ruled for centuries. Absolute space, absolute time, a fixed stage for the universe. It all seemed solid. Then came Einstein, 1905, a young patent clerk in Switzerland. He dared to question everything. Einstein asked a simple question. Why does light always move at the same speed? No matter the observer, no matter the source. This broke Newton's rules. Velocities no longer simply add. If you chase a beam of light, you'll never catch it. He proposed two postulates. First, the laws of physics are the same for all inertial observers. Second, the speed of light in a vacuum is constant for all observers. Radical, shocking, brilliant. Time could no longer be absolute. Space could no longer be fixed. Distance and duration depend on the observer. Moving clocks tick more slowly. Fast-moving rulers shrink. Mass increases with speed. Energy and mass are connected. E equals mc squared. This wasn't speculation. It was mathematics, and math that matched reality. Einstein's theory explained the Michelson-Morley result. No ether. No absolute frame. Light speed is constant everywhere. Special relativity redefined simultaneity. Two events that appear simultaneous to one observer may not be to another. The universe is stranger than intuition suggests. Yet, this new framework solved problems. Electromagnetism obeyed relativity. No inconsistencies. The cosmos made sense in a deeper way. It also predicted new phenomena. Time dilation, length contraction, mass-energy equivalence. Mass-energy equivalence. All was experimentally confirmed later. Special relativity became the foundation for modern physics, for quantum mechanics, for understanding space-time itself. Einstein had done the unthinkable. He shattered centuries of Newtonian certainty and built a new reality. The The universe no longer had a universal clock, no fixed stage, only a flexible space-time. This shift wasn't just theoretical. It affects GPS satellites, particle accelerators, high-speed travel, everywhere light and motion intersect. From Newton's absolute stage to Einstein's relative space-time, human understanding took a leap. We saw that space and time are not rigid. They bend, they flex, they depend on motion. And this was only the beginning. Special relativity paved the way for general relativity, for black holes, for cosmology, for a universe stranger than any science fiction. So remember this: the universe is not what it seems. Space and time are malleable. Reality is relative, and the laws of physics are the same for all. If this blows your mind, hit subscribe. Join the journey through space, time, and the deepest mysteries of the cosmos. Also, comment down the country and city from which you are watching and what the time there is right now. Einstein's postulates shook the cosmos. Light travels at a constant speed, always, no exceptions. But if light is constant, something has to give. Time, space, both. Enter Minkowski, 1908. Einstein's former professor. He had an idea. What if space and time aren't separate? What if they are one entity, 4 dimensions fused together? Space-time. Minkowski called it a union of space and time. Radical, brilliant, essential. Imagine a moving train. A clock on the train ticks more slowly than a clock on the platform. Distance shrinks along the train. Time stretches. Space-time explains it all. No longer is there absolute space. No longer is there absolute time. Only space-time relative to the observer. Minkowski's geometry allowed transformations from one observer's perspective to another. Mix space and time coordinates. Everything fits. This was more than math. It explained reality. GPS satellites rely on it. Without accounting for time dilation, navigation would fail. But why does the speed of light stay constant? It's baked into space-time itself. Space bends, time stretches. Observers always measure light the same. Visualize it like a fabric. Stretch it, move through it. Distances and durations warp, but light's speed remains untouchable. This constancy also explains mass-energy equivalence. E equals mc squared isn't just a formula. It's a statement about space-time geometry. Space and time are now flexible players, no longer the rigid stage Newton imagined. Events depend on the observer's motion. Simultaneity vanishes. 2 lightning strikes may appear simultaneous to one person. To another, moving relative to the first, they are separate. The universe becomes relative. Space-time dictates experience. Even momentum and energy must adjust. High-speed particles gain mass. Clocks tick differently. Distances shrink along motion. This is no thought experiment. It's reality, tested, measured, confirmed. Minkowski's vision gave Einstein's equations structure. Special relativity becomes more than abstract math. It's a tool to navigate the universe. Space bends, time stretches, all to preserve light's constancy. And this is just the beginning. If space and time can bend for speed, what about mass and gravity? That's the doorway to general relativity. So remember, light's constant speed forces space-time to bend. Distance and duration depend on you. Reality is not fixed. It moves with you. The universe is flexible, and we are just beginning to understand its rules. Einstein's special relativity shattered one core idea. There is no universal now, no cosmic clock ticking for everyone. Think about it. 2 events, lightning strikes, one on the left, one on the right. Are they simultaneous? Depends on who you ask. A person standing still sees one answer. A person moving past sees another. Reality splits. This is called the relativity of simultaneity. Events simultaneous for one observer may not be for another. Imagine two spaceships moving past each other at near light speed. Each has its own clock. Each sees the other's events differently. Each sees a different sequence. There is no universal now connecting both ships. Time is local, personal, relative. Even simple ideas we take for granted break down. What you consider the present is different from mine. The past, the future, they're observer-dependent too. Simultaneity links directly to space-time geometry. When you move, time and space mix. Minkowski's space-time diagrams make this clear. Lines representing events tilt depending on velocity. The faster you move, the more tilted your now line becomes. Observers slice space-time differently. This has real consequences. GPS satellites orbiting Earth experience a different time flow than we do. Their now is different. Without correction, navigation would be wildly off. But why does this matter for the universe? It means the universe has no absolute order, no global present. Cosmic simultaneity is gone. Past, present, and future exist in a block. All events are there in space-time. Our experience of flowing time is subjective. It's an emergent perception, not a universal property. Think of your life as a line in space-time. Your now moves along your world line. Another person's now moves along with theirs. The order of events may differ between world lines. Even causality is preserved. Nothing violates cause and effect locally, but the perception of simultaneity can shift. Past and future are relative, not absolute. This insight challenged centuries of Newtonian thinking. Time is not a river for all to follow. It's a personal journey, intertwined with space and motion. The implications ripple through physics. No universal tick, no cosmic present. The universe is a block, flexible and observer-dependent. Einstein's relativity forced us to rethink everything. Time is local, subjective, and inseparable from space. Simultaneity is a concept that bends with motion. We live in a universe where your now is not mine. Reality is stitched together differently for everyone. And understanding this is key to understanding the true nature of space and time. Einstein changed how we think about time. Space and time were no longer separate. But there was still a problem. How do we describe motion, events, and observers mathematically? Enter Hermann Minkowski, Einstein's former professor. He had a bold idea: combine space and time into one entity. Minkowski called it space-time, 4 dimensions, 3 of space, 1 of time. Everything exists in this 4D fabric. Imagine a 3D grid. Now add a timeline running through it. Every event has coordinates: X, Y, Z, and T. Your position in space and moment in time. Minkowski said, to transform between observers, mix space and time. If you move fast, your measurements of space change. Your measurements of time change, too. The faster you move, the more they mix. This was revolutionary. Space was no longer absolute. Time was no longer universal. Observers had their own space-time perspectives. Think of 2 observers moving past each other. They slice space-time differently. Their now lines tilt. Events simultaneous for one may be in the past or future for another. Minkowski's geometry clarified Einstein's equations. Special relativity could now be visualized. Time dilation, length contraction, simultaneity all became geometric consequences. Space-time isn't just math. It's the stage where physics happens. But unlike Newton's stage, it's flexible. Observers distort it with motion. This also paved the way for general relativity. If space and time can mix for moving observers, what happens when mass and energy curve space-time itself? Gravity could now be seen as geometry, not force. Minkowski famously said, henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. Space-time is independent, but it's intertwined with the events that occur. The universe is a 4D tapestry of happenings. Mass, energy, and motion shape it. This perspective changes everything. No universal simultaneity. No absolute distance. No absolute time. It also gives us new intuition. World lines. Paths of objects through space-time. Events. Points along those paths. Light travels along 45-degree lines in diagrams. Nothing can move faster than light in this fabric. Space-time diagrams became tools for understanding relativity. They show cause and effect, speed limits, and motion effects. They make abstract math tangible. Minkowski took Einstein's ideas and gave them geometric life. Space and time were no longer separate. They were two sides of the same coin. Understanding space-time is key. It's the foundation for black holes, gravitational waves, and cosmic expansion. It's the lens through which we see the universe. Minkowski didn't just unify concepts. He gave physics a new playground. One where space and time bend, mix, and interact. And where the stage itself becomes a player. Einstein wasn't done with relativity. Special relativity explained motion at constant speed, but gravity remained Newton's mystery. Newton saw gravity as a force, pulling objects across empty space. Distance mattered. But special relativity says distance and time are relative, so Newton's formula couldn't hold exactly. Einstein went back to the drawing board. What if gravity isn't a force at all? What if mass bends the very fabric of space-time? He realized, mass tells space-time how to curve. Space-time tells mass how to move. Objects follow the curves naturally. No force needed. Picture a trampoline. Place a heavy ball in the center. The fabric dips. Roll a marble nearby. It curves toward the heavy ball. That's how planets orbit the Sunday. Einstein published general relativity in 1915. Gravity is geometry. Space and time bend around mass and energy. Massive objects warp space-time. Smaller objects follow the curves. Time isn't immune. Clocks tick more slowly near massive objects. This is gravitational time dilation. Near a black hole, time almost stops. Space and time together, space-time, become dynamic. They stretch, shrink, and ripple. Not just a stage, but an actor in the universe. Einstein's equations predicted strange phenomena. Light bends around massive objects. Mercury's orbit shifts slightly over time. Gravitational waves ripple through space-time. Observations confirmed these predictions. 1919. Starlight bent by the sun during an eclipse. Einstein became a superstar. His theory wasn't just math, it described reality. Black holes emerged from general relativity, regions where space-time curvature is extreme. Escape velocity exceeds the speed of light. Time and space warp dramatically. Gravity is everywhere, but it's not pulling, it's shaping. Planets orbit stars along curved space-time paths. Galaxies swirl within their cosmic web. Even the universe itself is dynamic. Space-time can expand. The cosmos grows, stretches, and evolves. Energy, momentum, and geometry are intertwined. General relativity also reshaped causality. Signals can't travel faster than light. Cause precedes effect. But space-time curvature bends the rules subtly. Experiments keep confirming Einstein's vision. Atomic clocks on satellites tick faster than clocks on Earth. GPS systems rely on relativity for accuracy. Gravitational waves detected by LIGO, space-time literally rings. General relativity is profound. It tells us gravity is not a pull. It's the bending of space-time by mass and energy. It unites space, time, matter, and motion in one framework. This understanding sets the stage for cosmic phenomena. Black holes, neutron stars, warped universes. even the expansion of the universe itself. Einstein didn't just rewrite gravity. He showed that the universe is a living, flexible geometry. Every object traces paths on a curved, four-dimensional canvas. The cosmos is alive with bending, stretching space-time. And that's the true essence of general relativity. Gravity is geometry. Mass and energy shape reality itself. Space and time are no longer fixed. They are dynamic. Einstein's general relativity changed everything about gravity, but it also changed everything about time. Time isn't universal. It flows differently depending on where you are. Near a massive object, time slows down. This is called gravitational time dilation. Imagine two twins. One stays on Earth. The other travels near a black hole. The closer to the black hole, the slower their clock ticks. Years could pass for one twin, while only days pass for the other. Clocks are real-world proof. Atomic clocks in satellites tick faster than clocks on Earth. GPS systems must correct for this difference. Without relativity, your navigation would drift kilometers off each day. Time bends with space. Massive objects warp space-time. The stronger the gravity, the more extreme the warping. Near a black hole, a second on the surface might equal years far away. Even light is affected. Light climbing out of a gravitational well loses energy. Its wavelength stretches. This is gravitational redshift. Time and energy are intertwined in curved space-time. Black holes are the ultimate laboratory. Near the event horizon, time almost freezes. For a distant observer, anything falling in seems to slow down. Frozen, suspended in the fabric of space-time. Time dilation isn't just a theory. Experiments prove it. Clocks flown in high-altitude jets run slightly faster than ground clocks. Gravity pulls on time just as much as it pulls on space. Cosmic consequences are profound. Stars orbit black holes in extreme gravitational wells. Their light, stretched and delayed, reveals the intense warping of space-time. Even entire galaxies can cause measurable time effects through gravitational lensing. Think about the universe itself. Near neutron stars, white dwarfs, and black holes, time is different. Past, present, and future are no longer universal concepts. They depend on where you are and how fast you're moving. Einstein predicted this in 1915. 100 years later, we measure it precisely. Time is elastic, bending with gravity. Clocks don't agree. Not ever. The universe isn't a steady tick-tock. It's a flexible rhythm, shaped by mass and energy. Your heartbeat, your seconds, even the lifespan of stars are relative. Time dilation is everywhere, though subtle most of the time. Near massive objects, seconds stretch into minutes. Minutes stretch into hours. Time itself is a variable, not a constant. The cosmos reminds us, nothing is absolute. Time is no longer a background. It's a player in the cosmic stage. Curved, warped, and dynamic. The faster you move, the slower you age. The closer to mass, the slower your clock ticks. Gravitational time dilation challenges our intuition. It makes now relative. It makes aging relative. It makes the universe stranger than we ever imagined. And yet, this bending of time is not science fiction. It's real, measured, every day in satellites, telescopes, and particle experiments. Time isn't constant. It depends on space, motion, and gravity. In the universe, clocks never agree. And that's the profound lesson of gravitational time dilation. Black holes are the ultimate test of space-time. They aren't just massive, they're extreme. A black hole's gravity warps everything around it. Space bends, time slows, reality itself stretches. Imagine falling toward a black hole. You look at a distant star. It seems normal. Now, look at yourself. Time near the black hole moves differently. Seconds stretch into minutes. Minutes stretch into hours. The closer you get to the event horizon, the slower time passes for you compared to the outside universe. For a distant observer, it looks like you freeze in place, suspended at the edge, a frozen silhouette against the cosmos. Black holes aren't just weird, they're measurable. Astronomers track stars orbiting invisible objects. Their paths reveal immense gravity-bending space. Even light curves around black holes. This is gravitational lensing. Space is distorted, images twist, reality bends. Time dilation near black holes is extreme. A few hours for someone near the horizon might equal years far away. If you survived, you'd witness the universe age around you. A single trip could see civilizations rise and fall. Time is no longer shared, it's personal. Black holes also warp space itself. Distances stretch, paths curve. Even light cannot escape once it crosses the event horizon. This boundary isn't a wall, it's the ultimate point of no return. Beyond it, space-time collapses inward. Inside, theory predicts a singularity. Space and time break down. Density and gravity become infinite. Physics, as we know it, ceases. No known law can describe the core. Time may have no meaning there. Yet, black holes are not just destructive. They teach us. They show that gravity is geometry. Mass tells space how to curve. Curved space tells mass how to move. Time is woven into this cosmic dance. We've even detected gravitational waves from black hole mergers, ripples in space-time itself. These waves confirm that space and time can stretch and vibrate. Black holes are not isolated, they shake the universe with their motion. Black holes challenge everything we thought about reality. They show that time is malleable. They show that space can bend to extremes. They reveal a universe where the rules we know are stretched to limits. And yet, black holes are natural. Every galaxy may host a supermassive one. They're laboratories for extreme physics. Einstein predicted them. Schwarzschild solved the equations. Now we observe them directly. Time near a black hole is not just slower, it's personal. Your seconds are your own. Outside, observers measure a different universe. Black holes force us to rethink space, time, and reality itself. In the shadows of these cosmic giants, we see the true flexibility of space-time. Mass, motion, and gravity bend the very fabric of existence. Space is no longer empty. Time is no longer constant. Black holes aren't just cosmic monsters, they are mirrors. They reflect the true nature of space and time. Bend, warp, and slow. They show the universe's hidden rules. And they leave us with a haunting question. What is time, really, when the cosmos itself can freeze it? Einstein's equations didn't just explain black holes. They opened doors to wild possibilities. Solutions that sound like science fiction but are mathematically real. Wormholes are tunnels through space-time, a shortcut connecting distant points in the universe. Imagine stepping into one side of a tunnel and emerging light years away instantly. The fabric of space bends so sharply that distance almost disappears. Theoretically, these could even connect different times, past and future, folded like paper, waiting for traversal. But wormholes are fragile. They require exotic matter to hold them open. Matter with negative energy. We haven't found it yet, but the equations allow it. Mathematics doesn't care if nature says no, for now. Warp drives are another solution, popularized in fiction, but rooted in physics. Instead of moving through space faster than light, space itself moves. A bubble of space-time carries a ship along. Inside, the ship feels no acceleration. Outside, light speed limits don't apply because the ship isn't moving through space. It's space-time that moves. In principle, Einstein allows it. Energy requirements are massive, almost absurd. Curved universes take it further. Einstein's equations can describe universes that loop back on themselves. Parallel lines can converge or diverge. Space can bend in ways that defy our everyday intuition. A universe could be finite, but unbounded, like a 3D version of the surface of a sphere. Travel far enough in one direction, and you could return to your starting point. These exotic solutions reveal something profound. Space and time are flexible, not a static stage, not a rigid grid. They are shapes that can twist, bend, and fold. The universe is more than distances and durations. It's geometry in motion. Wormholes and warp drives also touch time. Some solutions allow closed time-like curves, paths that loop back on themselves. A traveler could, mathematically, return to their own past. Time travel isn't just fantasy, it's embedded in Einstein's math. Whether it can exist in reality is a different question entirely. These solutions challenge our concepts of causality. Could events influence the past? Could space-time itself allow paradoxes? Physicists explore these ideas with caution. The math is beautiful. The physics may not be real, yet these possibilities inspire exploration. They show that our universe is not limited to intuition. Reality at cosmic scales is stranger than fiction. Einstein's equations are a playground for imagination and for the limits of physics. Even if we never build a warp drive or traverse a wormhole, the mathematics teaches us about the universe. Curvature, geometry, and time aren't just abstract ideas. They define how the cosmos behaves, how matter moves, and how light travels. Exotic solutions remind us, space and time are not fixed. They are flexible, malleable, and sometimes bizarre. The universe allows possibilities far beyond ordinary experience, and in exploring them, we learn how deep the rabbit hole of reality really goes. Einstein predicted gravitational waves in 1916. Ripples in space-time, like tossing a stone into a cosmic pond. Massive objects moving generate them. But for decades, no one could detect them. They were simply too tiny, too faint. Then, in 1974, a discovery changed everything. Two astronomers, Russell Hulse and Joseph Taylor, were observing the sky. They used the massive 300-meter Arecibo telescope in Puerto Rico, scanning the universe for pulsars, rapidly spinning neutron stars. They found something extraordinary. A pulsar named PSR B 1913+16. It spun 17 times a second, like a precise cosmic metronome. But it wasn't alone. It orbited another neutron star, a dead stellar remnant. Two compact stars are dancing in a tight, fast orbit. Hulse and Taylor measured the pulsar's radio pulses. The pulses arrived like clockwork, ultra-precise. But over time, they noticed a change. The orbit was shrinking. The stars were slowly spiraling toward each other. Newtonian gravity couldn't explain this. Energy seemed to be leaking from the system. Where was it going? Einstein's gravitational waves provided the answer. The orbiting stars were radiating energy as ripples in space-time, exactly as predicted by general relativity. The match between observation and theory was remarkable. The orbital decay followed Einstein's calculations perfectly. Every tiny fraction of a second aligned with his predictions. For the first time, gravitational waves had indirect evidence. They weren't just math, they were real. The discovery shocked the physics community. Hulse and Taylor had confirmed a fundamental prediction of relativity. It was a triumph of theory and observation working together. In 1993, they won the Nobel Prize for this groundbreaking work. This discovery set the stage for the next leap. If gravitational waves could affect pulsars, could we detect them directly on Earth? Decades of engineering, planning, and innovation followed. The result? LIGO, the Laser Interferometer Gravitational Wave Observatory, a giant set of laser arms capable of measuring distortions smaller than a proton. Hulse and Taylor's pulsar proved it was worth the effort. Gravitational waves aren't science fiction, they ripple across the cosmos. They carry information about colliding black holes, merging neutron stars, and cosmic cataclysms. They are a new language of the universe. Think about it. The motion of two tiny dead stars, light years away, sending ripples that reach across the universe. Einstein predicted it a century ago. Hulse and Taylor detected it indirectly. Soon after, LIGO would detect it directly. Gravitational waves transformed physics. No longer do we rely solely on light to observe the universe. We can now hear it, sense its vibrations, and uncover phenomena invisible to telescopes. The Hulse-Taylor pulsar reminds us of the elegance of Einstein's universe. Curved spacetime, ripples traveling through the void, matter and energy are intertwined in a cosmic dance. It's a universe alive with motion, and with clever observation, we can catch its pulse. For decades, gravitational waves were a theory. Einstein predicted them in 1916. Indirect evidence came from the Hulse-Taylor pulsar. But could we detect them directly? Enter LIGO, Laser Interferometer Gravitational Wave Observatory. 2 facilities, thousands of kilometers apart, one in Washington, one in Louisiana. Giant L-shaped arms, 4 kilometers long. Lasers bouncing back and forth inside. Mirrors suspended, isolated from vibrations, looking for distortions smaller than a proton. In September 2015, history happened. A signal appeared on both detectors. A tiny wiggle, a whisper in the cosmos. The signal lasted a fraction of a second. It matched exactly the predicted waveform of colliding black holes. 2 black holes, 36 and 29 solar masses, spinning around each other at nearly half the speed of light, merging, releasing energy equivalent to 3 solar masses, all converted into gravitational waves. The waves travelled 1.3 billion light-years. And finally, they reached Earth. Scientists stared at the data. They checked, rechecked, triple-checked. No error, no interference. It was real. Einstein's ripples were here. The discovery was monumental. It confirmed the existence of gravitational waves. It confirmed black hole mergers. It confirmed a century of Einstein's predictions. It opened a completely new way to observe the universe. No telescope needed. No light required. LIGO listens to the universe. It detects vibrations in space-time itself. Since 2015, LIGO has detected dozens of events. Black holes colliding. Neutron stars are merging. Even a neutron star merger with a gamma-ray burst. We now have gravitational wave astronomy, a whole new spectrum of cosmic observation. LIGO is more than an experiment. It is proof of human ingenuity, engineering marvels, precision beyond imagination, mirrors floating in a vacuum. Lasers measure changes smaller than 1,000th of a proton's width. And the implications are staggering. We can explore dark corners of the universe. We can test Einstein's relativity in extreme conditions. We can probe the birth of black holes. We can begin to understand the most violent events in the cosmos. Gravitational waves carry information that light cannot. They penetrate dust, gas, and everything in between. They reveal the invisible choreography of massive objects. And LIGO listens, silently, patiently, waiting for the next cosmic whisper. This is more than science. It is a revolution in perception. We no longer just see the universe. We can feel it. We can hear it. We can measure its heartbeat. LIGO proves that space and time are alive. They bend, ripple, and vibrate. And with careful eyes and ears, we can finally understand their subtle song. The universe is not static. It never has been. Galaxies are moving away from each other, not because they are flying through space, but because space itself is expanding. Edwin Hubble discovered this in 1929. He measured galaxies and their redshift. The farther a galaxy, the faster it recedes. Hubble's law. Velocity equals distance times a constant. The universe is stretching, growing, unfolding. Imagine a balloon. Dots on its surface are galaxies. Blow up the balloon. Dots move apart, not because they crawl along the surface, But because the surface expands beneath them, space is the balloon, and the dots are galaxies. This expansion changes our understanding of space. Space is no longer a passive stage. It has dynamics. It bends, stretches, and ripples. Galaxies are carried along. Some are held together by gravity. Others drift freely into the cosmic void. The speed limit of light is not broken. Galaxies can recede faster than light, not moving through space, but carried by space itself. The universe becomes less dense over time. Empty space grows between cosmic islands. Expansion also affects energy. Photons stretch as they travel. Their wavelengths lengthen, and energy decreases. Cosmic redshift is a direct result. Energy conservation, once sacred, is more subtle now. The expanding cosmos challenges traditional physics. Dark energy is the mysterious driver. It pushes space apart, accelerating expansion. Galaxies in faraway regions will eventually disappear. Their light will never reach us. The observable universe shrinks even as space grows. Expansion shapes the arrow of time. The universe moves from dense, hot beginnings to sparse, cold futures. Entropy increases as galaxies drift apart. Matter spreads, stars burn, black holes form. Space itself is tied to the flow of cosmic history. Yet expansion is uneven. Local gravity resists. Our Milky Way and nearby galaxies remain bound. Clusters form, filaments weave the cosmic web. Space grows between these islands of matter. The expanding universe rewrites perspective. Distance is not static. Time is not universal. Space is alive, dynamic, and stretching constantly. Cosmic distances are not measured in miles, but in the growth of space itself. This is the universe we inhabit, a cosmos in motion, growing silently. Galaxies drift, stars burn, and time marches forward. Space is not empty. It is the very fabric that carries the universe toward its future. And we are just passengers, drifting along with it. Energy, a fundamental rule of physics. In our everyday life, it never disappears. Cars burn fuel. Light bulbs shine. Momentum and energy are conserved. Change a system, and the total energy remains constant. But the cosmos plays by different rules. The universe is expanding. Space itself grows. Galaxies drift apart. Photons stretch. Light loses energy as it travels. Redshift isn't just a shift in color, it's energy lost to expansion. This is not a small effect. Over billions of light years, the energy drain becomes enormous. Energy is not disappearing locally, it's being diluted globally. The universe has no cosmic battery to compensate. Expansion breaks the classical symmetry that normally enforces conservation. Why does symmetry matter? Emmy Noether taught us this. Physics stays the same if we shift location. Momentum is conserved. If physics doesn't change over time, energy is conserved. But expanding space breaks this uniformity. Time itself is no longer symmetric. Energy, as a universal constant, loses its grip. Dark energy complicates the picture. It pushes the universe apart. It accelerates the expansion. The energy associated with space itself grows. Where does that energy come from? From nowhere, there is no outside. Cosmic energy is not like energy in a closed system. Gravitational potential adds another twist. Galaxies slow down relative to the expanding space. Their kinetic energy decreases. Stars form, black holes grow. Energy moves around, transforms, but global accounting is impossible. Even photons, the messengers of light, feel the change. Traveling across billions of years, their wavelength stretches, energy drops, the universe cools. The cosmic microwave background is a reminder. Energy is smeared across a growing, expanding cosmos. This doesn't mean physics is broken. It means our classical rules are limited. Local physics obeys conservation. Globally, in a dynamic universe, energy is a trickier concept. Energy conservation is not absolute when space itself expands. The implications are staggering. The universe evolves. Energy is redistributed in ways Newton never imagined. Stars burn, galaxies collide, light stretches. The cosmos is dynamic, alive, and fundamentally different from our intuitive rules. So, as we watch the universe grow, remember this: energy is no longer a simple accounting problem. It's entwined with the stretching of space. It's a dance between matter, radiation, and the expanding void. In the dynamic cosmos, energy conservation is a local rule, not a global law. Imagine the universe as a giant book. Every page is already written. Past, present, future, all exist. The story isn't unfolding, it's already complete. This is the block universe, a natural consequence of Einstein's relativity. No absolute now, no universal clock. Time is a dimension, like space. All events are laid out. Your birth? Already a page. Your graduation? Already a page. Even the distant future? Already there. The universe is a fixed, four-dimensional structure. Particles move along world lines. A world line traces a particle's path through space and time, from birth to death, from past to future. You are a bundle of world lines, tied together into a single knot of existence. When you're gone, the world lines scatter again. The block universe raises a troubling question. If everything is already there, what is free will? Do we really choose, or do we just follow pre-written paths? Is your life a predetermined route, like a train on tracks? Physics doesn't answer. It only maps the tracks. Relativity complicates things further. Two observers, moving differently, experience different nows. What one sees as present, the other sees as past or future. No universal present, no cosmic now. Time becomes relative. Microscopic laws of physics don't care about direction. Electrons repel. Gravity pulls. Strong nuclear forces bind nuclei. Run the movie backward, and the interactions look perfectly normal. At this scale, time has no arrow. But our macroscopic world does care. Ice melts. Stars explode. Coffee cools. Entropy increases. The arrow of time emerges from countless atomic interactions, not from fundamental laws. The block universe forces a radical perspective. Time is like space, already mapped. The past isn't fading. The future isn't unknown. All is laid out in a four-dimensional continuum. Yet, we experience life differently. Moments flow. We remember the past. We anticipate the future. Our consciousness slices the block universe into an illusion of now. Cosmology adds another twist. The universe began with the Big Bang. It had a low entropy starting point. This initial smoothness sets the arrow of time. Even in a block universe, the flow of entropy distinguishes past from future. Philosophers and physicists debate endlessly. Is the block universe real, or is it a mathematical framework, hiding the dynamic nature of reality? Some propose quantum processes carve out a now, instant by instant. Others suggest the universe is fully predetermined. Either way, the block universe challenges our intuition. Time is not a river, not a flowing arrow. It's a landscape, a four-dimensional block, and we navigate it, unaware of the full map. Imagine a single electron. It exists in space and time, but how do we track it? Enter the world line. A world line is a particle's personal path through the four dimensions of space-time. From its birth to its death, every instant is a point on this line. It's like a thread weaving through the cosmic fabric, not just electrons. Every particle, every planet, every photon has a world line. Even you. You are a bundle of countless world lines, tangled together. This bundle defines who you are in space-time. World lines show the relativity of motion. Two observers moving differently see different slices of now. Your present might be someone else's past. Yet the world line itself exists unchanged. It's absolute even when time is relative. World lines explain gravity in Einstein's universe. Massive objects bend space-time. World lines curve around them. Planets orbit stars because their world lines follow curved space-time. Not because of an invisible force, but because the geometry dictates the path. World lines also reveal the limits of motion. No world line can exceed the speed of light in a vacuum. Trying to push a particle faster bends the line toward impossibility. Even light itself follows a straight world line through curved space-time. Now imagine tracing your life as a world line, from your first breath to your last. Every decision, every step, every heartbeat is a point on that line. But in a block universe, your line is already set. You don't move along it, you exist along it. World lines can twist in strange ways. In theoretical models, some curves loop back, travel along these, and the past could meet the future. Closed time-like curves. Yes, this is the physics behind time travel possibilities. Though our universe may not permit it, the math allows it. World lines also explain interactions. When two electrons repel, their world lines approach, bend, and move apart. Even if we play the movie backward, physics works the same. At the microscopic level, the laws are time-symmetric, yet collectively, with billions of particles, we see entropy increase, giving the arrow of time. Understanding world lines is essential to understanding space-time itself. They aren't just paths, they are maps of existence. Every point encodes position and moment. Every curve encodes the influence of mass and energy. Every intersection tells a story of collision, force, or interaction. So the next time you think about space or time, imagine your own world line, a thread weaving through the universe, your personal journey in the fabric of reality. And realize you are more than just matter. You are a pattern in space-time itself. If you want to dive deeper into how world lines shape the universe, and maybe even hint at time travel, make sure to subscribe now, because the journey is just beginning. Look closely at the universe. At the tiniest scales, the rules are surprisingly simple. Electrons, quarks, photons all follow strict laws. These laws are the microscopic forces: electricity, magnetism, the strong force, the weak force. They dictate how particles move, interact, and transform. But here's the kicker: these forces don't care about time. Forward or backward doesn't matter. Run the clock backward. The equations still work. Imagine two electrons approaching each other. They repel, then they move apart. Play the video in reverse. They still repel. Physics doesn't complain. Microscopic interactions are time-symmetric. No arrow of time exists at this level. No preferred direction. The universe doesn't tell these particles which way is forward. Gravity, at the particle level, is similar. In Einstein's equations, time can flow either way. Photons, planets, black holes, they all obey reversible rules. Even the weak nuclear force misbehaves slightly, but mostly symmetry holds. Now step back. Zoom out to the macroscopic world. Coffee cools, ice melts, stars explode. Time suddenly has a direction. Entropy increases. Things fall apart, not together. Here, an arrow of time emerges. Why the difference? How does time symmetry at the tiny scale become irreversible behavior at the large scale? This is the puzzle physicists call the emergence of time. It all begins with numbers. Atoms are countless, billions, trillions, interacting simultaneously. Individual interactions are reversible. Collectively, patterns emerge. The system trends from order to disorder. Enter statistical mechanics. Ludwig Boltzmann showed that entropy isn't magic. It's probability. Highly ordered states are rare. Disordered states dominate. Even though each particle can move backward, the whole system naturally drifts toward disorder. This explains why eggs break but never spontaneously reassemble. Why coffee cools instead of heating on its own. Time's arrow is statistical, not fundamental. Information plays a role too. To reverse a system perfectly, you'd need to know every particle's position and momentum. Even one unknown disrupts perfect reversal. The universe doesn't provide that information, so the arrow persists. Microscopic symmetry also hints at deeper mysteries. Time might be emergent, not fundamental. Perhaps the laws of physics themselves don't prefer forward motion. The now we experience arises from collective behavior, from billions of microscopic interactions summing together. Even in our own bodies, this happens. Molecules interact, and chemical reactions proceed. Forward is forward, because probability favors it. Yet the particles obey reversible rules. This symmetry is central to quantum mechanics. Superpositions, entanglement, and wave functions all respect time symmetry. But measurement, decoherence, and interaction with the environment produce apparent irreversibility. Microscopic forces may not care about time, but we care. Our clocks tick forward. Our lives unfold in one direction, and that direction is written in the statistical patterns of countless particles. The universe is full of paradoxes. At the tiniest scales, time is a neutral backdrop. At our scale, it flows like a river. Understanding this bridge between scales is key. Time symmetry at the microscopic level versus time's arrow at the macroscopic level. This is the subtle dance of the cosmos. And if you want to explore more about how time emerges, how entropy guides it, and how the universe weaves the microscopic into the macroscopic, stick with us. Because the story of time is far from over. Time feels real. Seconds tick, minutes pass. We remember the past, we anticipate the future, but at the microscopic scale, time has no direction. So where does our arrow of time come from? It begins with entropy. Entropy measures disorder. The universe prefers disorder. High probability states are disordered. Low probability states are ordered. Simple, natural, unstoppable. Imagine a room full of gas molecules. Initially, all molecules are in one corner. Ordered. Low entropy. They move, spread, mix. Random collisions. Chaotic dance. Eventually, gas fills the room. Disorder dominates. Entropy increases. The microscopic interactions are reversible. Electrons repel. Photons move. Run the film backward. Nothing breaks physics. But collectively, the system drifts toward disorder. The arrow emerges from statistics. Our universe started in an extremely low entropy state. Smooth, dense, hot, energy tightly packed. Gravity had work to do. Matter clumped. Stars formed. Galaxies spun. Entropy began its climb. Every macroscopic process now follows this climb. Coffee cools. Stars explode. Ice melts. Order becomes disorder. Time's arrow points forward. It's a statistical certainty, not a fundamental law. Information is key. Every interaction erases details. Each forgotten piece adds to the entropy ledger. This is why the past is remembered. The future is uncertain. Even life depends on it. Cells metabolize energy. Stars burn hydrogen. Planets orbit. All increase entropy. Time's arrow is imprinted on everything. Thermodynamics and statistical mechanics explain why. Microscopic symmetry, yes. Reversible laws, yes. But large numbers of particles? Irreversible outcomes. Order becomes disorder. Chaos accumulates. The macroscopic arrow is everywhere, not in individual particles, not in isolated forces, but in the collective. The forest, not the tree. Society, not the person. Universe, not the atom. Entropy sets the direction. Time flows as a consequence. We experience it linearly, yet the fundamental equations do not. So when you feel time pass, remember, it is not absolute. It is emergent, born from probability, from countless microscopic events, from the universe climbing from order to disorder. And this arrow connects to everything: our memories, our causality, our lives. It is the invisible hand guiding the macroscopic world. Time is not written into the laws themselves. It is written into the structure of the universe. The arrow of time is subtle. It is statistical. It is everywhere. It is in you, in me, in the cosmos. The microscopic may ignore it, but the macroscopic cannot escape it. The universe began, not gradually, not slowly, exploded from a singular point, hot, dense, intense, everything packed together. And yet, it was extraordinarily smooth, almost perfectly uniform, matter evenly spread, energy tightly balanced. This smoothness is strange. Very low entropy. Why does it matter? Entropy drives the arrow of time. High entropy is disorder. Low entropy is order. The universe began in an ordered state, a special state. Against the odds, gravity complicates this picture. Gravity loves clumps. Matter should collapse. Stars, galaxies, black holes form. The initial smoothness gave gravity room to work, to create structure, to shape the cosmos. Without low entropy at the start, no stars, no planets, no life, no arrow of time as we know it, no past, present, or future to experience. This is a cosmic puzzle, the odds of the universe beginning in such a low entropy state. Astronomer Roger Penrose calculated 1 in 10 circumflex, 10 circumflex 123, a number so vast it defies imagination. Clearly, something special happened at the Big Bang, and this sets the stage for everything. Entropy starts low, entropy increases, time flows forward, the universe expands, galaxies drift apart, stars burn, life evolves. This initial condition links microscopic physics and cosmic evolution. Particles obey reversible laws. Electrons repel, photons move. Yet the universe's birth gives a direction to all processes. From the tiniest atom to the largest galaxy, the arrow of time is written into the cosmos itself. Cosmology meets thermodynamics. The Big Bang's low entropy is not accidental. It defines the possibility of order in the universe. It allows causality, memory, and structure to exist. And for us, it explains why we can remember the past, why the future feels uncertain, why life can arise at all. The universe is special, not random, not generic. Its birth carried the cosmic fingerprint of order. From this fingerprint, the arrow of time unfurls. From this low entropy beginning, everything we experience emerges. So, the next time you look at the stars, remember their existence and yours began with this extraordinary condition. The universe started special. Low entropy set the rules. Time's arrow began its journey. And everything we know stems from that one smooth, ordered moment. Time travel. Not science fiction. Not fantasy. At least, not entirely. In 1944, a Dutch mathematician named Willem Jacob van Stockham explored Einstein's equations. He considered a rotating universe, a cosmos that spins, and what he found was startling. In a rotating universe, space and time twist. Particles moving through it follow curved paths, paths that loop back on themselves. He called these closed time-like curves, essentially time travel paths. A particle could leave the past, move forward, and eventually return to its own past. Van Stockham's universe was peculiar. It was not like ours, but mathematically, it worked. It revealed that Einstein's relativity allowed bizarre possibilities. A few years later, in 1949, Kurt Gödel rediscovered this idea. Gödel, the logician famous for his incompleteness theorem, turned to cosmology while at Princeton. He found a similar rotating universe solution, and it too allowed closed time-like curves. Gödel's universe was extreme. Time loops existed everywhere, past, present, and future intertwined. Causality, the idea that cause precedes effect, became flexible. In such a universe, could you travel to the past? Could the future influence the present? Mathematically, yes. Physically, probably not. These solutions shocked Einstein. Gödel even presented his work to him as a birthday gift. Einstein admitted it was disturbing. Relativity, he realized, was far stranger than he imagined. But the important takeaway isn't that time travel is real, it's that space-time itself can be warped in extreme ways. Mass, rotation, and gravity bend both space and time. Under the right conditions, the very structure of reality could create loops through time. And while our universe does not appear to rotate like Gödel's model, these solutions remain valuable. They expand the limits of what's possible within Einstein's equations. They force physicists to confront the relationship between time, causality, and geometry. Rotating universes and closed time-like curves highlight a deeper truth. Time is not absolute. It can stretch, bend, and even loop under extreme circumstances. Einstein's relativity is more than a theory of motion. It's a theory of the fabric of reality. From Van Stockham to Gödel, one thing is clear. Mathematics allows possibilities that stretch the imagination. Space and time are not fixed. They are dynamic, flexible, and surprisingly strange. And as we explore these ideas, we begin to see that the universe is far more mysterious than everyday experience suggests. Time might not flow as we think. Space might not exist in the way we assume. And somewhere, in the equations, reality hints at its deeper secrets. Time travel, a dream of science fiction, a puzzle for physicists. Einstein's equations allow bizarre possibilities. Van Stockham and Gödel showed rotating universes with closed time-like curves. A particle could, in theory, return to its own past. But what about humans? Enter wormholes, hypothetical tunnels through space-time, two ends connected across space, and possibly across time. In theory, entering one end could send you to the other instantly, or even into the past. Add spinning black holes to the mix. Kerr black holes twist space-time. Their spin drags space and time around them. Mathematical solutions suggest shortcuts through time might exist. Could someone travel forward or backward along these paths? Physics allows equations. Reality imposes limits. Energy requirements are astronomical. We would need incredible mass, perfect stability, and control over space-time. Tiny disturbances could collapse the tunnel. Wormholes might pinch closed in an instant. And then there's the paradox problem. Traveling to the past raises questions. Could you change history? Could you prevent your own existence? The famous grandfather paradox arises. Kill your grandfather before your parent is born. What happens then? Some theories try to solve it. The Novikov self-consistency principle says, events along closed time-like curves are self-consistent. You might travel back, but you cannot change history in a way that creates contradictions. Others propose multiple timelines. Traveling to the past might branch reality. A new timeline forms, leaving the original intact. Even with solutions, practical time travel remains far beyond reach. Space-time manipulations require energies we cannot harness. Our universe might forbid shortcuts in reality, despite allowing them in theory, yet the theoretical work is invaluable. It teaches us about space-time, gravity, and causality. It stretches the imagination. It pushes physics beyond everyday experience. Time travel also forces us to ask deep questions about reality. Is time linear or flexible? Are past, present, and future fixed? Do paradoxes indicate limits of physics or limits of understanding? In the end, time travel is a theoretical possibility. Equations allow it. Reality may not. Paradoxes warn us. Energy requirements block us, but the dream lives on, from wormholes to spinning black holes, from Gödel's loops to Novikov's consistency. Time travel remains a window into the strange, counterintuitive nature of space-time. And as our understanding deepens, we may discover whether these theoretical doors through time are mathematical curiosities, or gateways to a deeper reality. Quantum mechanics, a world so small it defies intuition. Particles that act like waves, waves that act like particles. Uncertainty at its core. In the quantum world, space-time initially seemed fixed, a backdrop, a stage where fields and particles performed their strange dance. Electrons oscillating, photons zipping, quarks jittering inside protons, all occurring on a Newtonian stage. But Einstein had already bent space-time with relativity. Special relativity warped time and space. General relativity made them dynamic, curved by mass and energy. So, quantum mechanics faced a dilemma. How can fields act on a stage that is itself changing and flexible? Physicists developed quantum field theory. QFT treats particles as excitations of underlying fields. Electrons emerge from an electron field. Photons emerge from the electromagnetic field. Each field pervades space-time, and the stage itself remains largely fixed. This works perfectly for small-scale interactions. Electromagnetism, weak and strong nuclear forces. Calculations match experiments to extraordinary precision, but gravity remains the odd one out. Curved space-time from general relativity cannot easily fit into the QFT framework. The stage bends, but the quantum fields want a flat, fixed stage. A fundamental clash emerges. Even so, QFT teaches us profound lessons. Particles are not little billiard balls. They are disturbances in fields. Empty space is never empty. Vacuum fluctuations spawn particle-antiparticle pairs. Space-time is filled with activity. Here's the twist. The energy of these fluctuations curves space-time. Quantum fields influence the geometry of space and time. The stage begins to react to the actors, not just host them. Gravity and quantum mechanics whisper to each other, but we cannot yet fully unify them. Some attempts push boundaries further. String theory imagines particles as tiny vibrating strings. Each vibration corresponds to a different particle. Strings live in multiple dimensions. Space-time itself may emerge from the relationships between strings, not fixed, not static, not fundamental, but emergent. Then there's loop quantum gravity. Space-time is granular. Space and time are made of discrete chunks, like atoms of space-time itself. At this Planck scale, the continuum of relativity breaks down. Quantum mechanics dominates the very fabric of reality. In all cases, space-time is no longer a passive stage. It interacts, responds, and even emerges from the quantum world. Fields and geometry are entwined. Energy shapes space. Space shapes energy. Everything is relational. And yet, our macroscopic perception smooths over this complexity. Planets orbit stars. Clocks tick. Light travels. We see space-time as continuous, uniform, and reliable. But underneath, the quantum stage is alive with uncertainty and granularity. Quantum mechanics forces us to reconsider. Is space-time fundamental, or is it just a convenient approximation emerging from deeper interactions? Every particle, every field, every fluctuation hints at something profound and unseen. Our universe may be a stage, but one that builds itself from the quantum drama upon it. Space-time and fields are inseparable. The macro and the micro are entwined, and only by studying both can we glimpse the true architecture of reality. By the 1920 seconds, quantum mechanics was exploding. Schrödinger, Heisenberg, Bohr. The quantum world was strange, probabilistic, and powerful, but it had a problem. It ignored Einstein. Relativity had already changed space and time, yet quantum equations were still running on a fixed stage. Enter Paul Dirac, a man of few words, a mind of endless depth. Colleagues joked he spoke 1 word per hour. But when it came to equations, his thoughts moved at light speed. Dirac asked a bold question. What if quantum mechanics obeyed special relativity? If the speed of light is absolute, then our equations must respect it. He began to tinker. Sundays, alone, walking, thinking, calculating. He sought an equation that married relativity with quantum theory. In 1928, it appeared. Dirac's equation, elegant, powerful, perfectly consistent with special relativity. And it explained the electron, spin, magnetic moment. Oddities that had puzzled physicists suddenly made sense. But there was a surprise. Dirac's equation had 2 solutions. One was the electron, negative charge, familiar. The other? Unknown, a positive solution. Dirac wondered, could it be the proton? No, too massive. Instead, he predicted a new particle, the positron, the first antimatter particle, same mass as the electron, but opposite charge. A revolutionary prediction before it was even observed. And observed it was, in 1932, by Carl Anderson. Antimatter leaped from theory into reality. Dirac's equation had transformed physics. Not just electrons, every particle has an antiparticle. Quarks, positrons, antiprotons, matter and antimatter, twin sides of the same coin. Dirac's insight went further. It laid the foundation for quantum field theory. Particles are excitations in fields. Fields obey relativity. Interactions respect the speed of light. The microscopic world is now relativistic and quantum at the same time. But questions remained. Gravity? Still left out. Curved spacetime? Not yet compatible. Dirac's equation worked on a flat stage. Quantum fields danced on a mostly static spacetime. Merging gravity with quantum theory remained elusive. Still, Dirac's equation revealed a profound principle. Relativity and quantum mechanics are not enemies. They can combine, and when they do, new realities emerge. Particles we never imagined, properties we never expected, antimatter, quantum fields, spin all predicted mathematically before we saw them. Dirac's work also hinted at the deeper structure of the universe. Symmetry, duality, conservation laws. The universe is not chaotic at its core. It obeys deep, beautiful mathematics. And sometimes, the mathematics leads reality. Through Dirac, we see a truth. Quantum mechanics and relativity are 2 sides of the same coin. One describes the tiny, one sets the rules for speed and space. Together, they hint at a universe stranger than we can fully comprehend. And antimatter reminds us. Reality may seem solid, predictable, and one-sided, but the universe is balanced. Every electron has a positron. Every action echoes. And every equation may reveal a universe yet unseen. Dirac gave us more than a particle. He gave us a framework, a blueprint, a vision of a relativistic quantum world. And in this world, matter and antimatter exist, fields interact, and the cosmos obeys a hidden, elegant order. Quantum field theory sounds complex. It is, but it's also the language of the universe. After Dirac, physicists realized something profound. Particles aren't just tiny balls. They're excitations in fields. The universe is a vast field of possibilities. Electrons, quarks, photons, they are all ripples in their respective fields. Think of a calm pond. Drop a stone, ripples spread. That's a particle. Quantum field theory says the same thing, but the pond is the entire universe. Every particle has a field. Electrons, photons, gluons, neutrinos, even the Higgs. Fields interact, particles collide, matter forms, matter decays. It's all a cosmic dance of fields. and it's relativistic. Every interaction respects the speed of light. Nothing can exceed it. Nothing breaks the rules of special relativity. Even quantum weirdness bows to this cosmic speed limit. Feynman diagrams emerged. Simple drawings, hiding incredible mathematics. They show particles colliding, transforming, annihilating. Electron meets positron, boom, 2 photons. Quark scatters off gluon ripples in the strong force field. Elegant, visual, powerful. QFT is more than particles. It's a framework for forces. Electromagnetism, photon field. Weak nuclear, W and Z bosons. Strong nuclear, gluon field. Gravity, still a mystery, but everything else, captured mathematically. Renormalization tamed infinities. Early quantum equations blew up. Numbers went to infinity. Physicists panicked. Dirac would have raised an eyebrow. But Feynman, Schwinger, Tominaga, the infinities were controlled. The theory became predictive, and nature agreed. Experiments confirmed it. Particles predicted decades before being observed. Antimatter, W and Z bosons. Higgs boson, QFT isn't speculation. It's tested, measured, precise. Quantum field theory also introduced the vacuum as dynamic. Empty space isn't empty. It's full of fluctuations. Virtual particles pop in and out. The vacuum has energy. Even nothingness is alive. QFT is the playground of modern particle physics. Colliders smash particles at incredible speeds. Detectors record every trace. Physicists decode the ripples. They understand the rules of the cosmos at the smallest scales. But there's a catch. Gravity doesn't fit. Curved spacetime resists this framework. QFT assumes a fixed stage. Einstein's general relativity says the stage itself bends and warps. So far, no one has reconciled the two. Still, QFT remains powerful. It underlies the Standard Model. It explains most of reality, from the tiniest quark to the Higgs field that gives mass, from particle collisions to quantum electrodynamics. It's a playground, yes, but also a map, a blueprint of how the universe behaves at its most fundamental level. It shows the elegance hidden in the chaos, the symmetry behind complexity, the rules beneath the apparent randomness. Quantum field theory is more than math. It's the story of existence itself. Particles, forces, interactions, and the subtle hum of empty space. A universe coded in fields, and we are learning to read it. QFT is the modern particle playground. Every discovery, every collider run, every calculation brings us closer. Closer to understanding the cosmic machinery behind reality. Closer to uniting it with gravity. Closer to a theory of everything. Quantum field theory works beautifully. Relativity works beautifully. But try to combine them? Chaos, frustration, years of brilliant minds hitting a wall. QFT assumes a fixed stage. Particles dance on it. Fields ripple. Collisions occur. Everything is predictable, at least mathematically. Gravity, though? Einstein's universe is dynamic. Mass and energy bend space and time. The stage is no longer fixed. It moves, stretches, curves. Every object influences the stage itself. And this is where problems begin. Try to apply quantum rules to curved spacetime. Equations explode. Numbers go to infinity. Not small infinities, catastrophic infinities. The mathematics collapses. Physicists have tools to tame quantum infinities. Renormalization works for QFT. It fails miserably when spacetime bends. Black holes make it worse. Near a black hole, spacetime curves intensely. Quantum effects become enormous. The singularity, the point of infinite density, defies every known law. Space and time end, and so does the predictability. We lack a theory to describe the quantum heart of gravity. Physicists have tried many paths. Loop quantum gravity, String theory, M theory. Extra dimensions. All attempts are bold, elegant, beautiful. None are complete. None fully unite the macroscopic gravity of general relativity with the microscopic quantum world. The clash is fundamental. Quantum mechanics is probabilistic. Gravity is deterministic. Particles pop in and out of existence. Space and time bend continuously. How do you reconcile probabilities on a stage that itself is uncertain? Some approaches treat gravity as just another field. Gravitons, hypothetical quantum particles of gravity. Mathematically appealing, experimentally invisible. So far, we have no direct evidence. Others try to quantize space-time itself. Loop quantum gravity says space-time is made of discrete chunks, tiny atoms of space and time. Beautiful idea, but extremely hard to test. No experiment has yet confirmed these predictions. String theory takes a different route. It replaces particles with vibrating strings. Different vibrations give different particles. Extra dimensions, hidden from view, stabilize the theory. It unifies all forces almost. Gravity fits naturally, but it's unproven, and it predicts an enormous landscape of possible universes. We don't know which one is ours. The failure to merge gravity and quantum mechanics is not for lack of trying. Every leading physicist of the 20th and 21st century has wrestled with this. Einstein spent decades searching for a unified field theory. He never succeeded. Today, we understand the problem more clearly. The universe at the smallest scales behaves quantumly. The universe at the largest scales bends relativity. Somewhere in between, the rules clash, and we still do not know the language that unites them. Yet failure is not defeat. Every attempt teaches us something. Every partial theory guides experiments. We glimpse the boundaries of our understanding. We explore black holes, gravitational waves, and the early universe. We measure particle collisions at unimaginable energies, all trying to uncover the missing connection. The ultimate lesson? The universe is stranger than we can fully imagine. Gravity and quantum mechanics work separately. Together, they remain an unsolved riddle. And maybe, just maybe, solving it will redefine space, time, and reality itself. The quest to unite gravity and quantum mechanics didn't stop with failure. Physicists didn't give up. They got creative. Extreme, almost surreal creativity. Enter string theory. Not particles, but tiny vibrating strings. Each vibration produces a particle. Electron? Vibration mode 1. Photon? Vibration mode 2. Quarks, gluons, neutrinos all emerge from the strings. Strings are tiny, way smaller than an atom, way beyond our ability to directly observe, yet mathematically elegant. Gravity appears naturally. Gravitons, the quantum particles of gravity, arise automatically. Finally, a step toward unification. But there's a catch. To make the math work, strings need extra dimensions. Not just the 3 of space and 1 of time. 10 dimensions in string theory, 11 in M theory, more than we can see, touch, or imagine. These dimensions are hidden, curled up tightly. We perceive only the familiar 4. M theory emerged as a broader framework. Strings become membranes, brains. Some float in higher dimensional space. Our universe, perhaps just a 3D brain in a 10D or 11D cosmos. Collisions of brains could explain the Big Bang, cosmic evolution reimagined. Gravity might leak into extra dimensions. This could explain why it's weaker than other forces. String theory and M theory are beautifully consistent. They avoid the infinities that plague other attempts. They include all fundamental forces. They unify electromagnetism, weak and strong nuclear forces, and gravity. Everything, in principle, is described by one mathematical structure. But there's a problem. They are hard to test experimentally. The strings are too tiny. Extra dimensions are too small to detect. We can't probe Planck-scale physics yet. Predictions exist, but mostly in realms beyond our current experiments. Still, these theories have power. They inspire new mathematics. They hint at connections between black holes and quantum mechanics. They suggest space and time may be emergent, not fundamental. The cosmos might be a hologram. Reality could arise from deeper layers of information. Other approaches focus on loop quantum gravity. Instead of extra dimensions, it quantizes space-time itself. Space and time are made of tiny atoms or loops. The universe becomes a granular mesh at the Planck scale. Smooth space-time is an illusion. Gravity emerges from these quantum loops. No strings, no brains, just space-time itself. Both approaches share a radical insight. The universe is far stranger than our senses suggest. Space and time are not absolute. They may be emergent, discrete, and deeply connected to quantum information. Yet neither is complete. String theory is elegant, but untested. Loop quantum gravity is precise, but limited. The final theory remains elusive. Still, these modern approaches redefine how we think about the cosmos. They expand our imagination. They force us to question the nature of reality. They suggest that space, time, matter, and forces are all part of a deeper, unified structure. We are not done yet. The quest continues. One day, one breakthrough might finally unite gravity and quantum mechanics. And when it does, our understanding of space, time, and the universe will be transformed forever. Gravity and quantum mechanics don't play nice. String theory tries one approach. Loop quantum gravity takes another. No extra dimensions, no strings, just space-time itself. Imagine space-time is a fabric, smooth to the eye, but zoom in far enough. It's made of tiny loops, a mesh, a weave, granular, quantized. Each loop is a quantum of space, tiny, indivisible. No smaller part exists. Together, they form a network. The universe becomes a quantum lattice. Time, too, is woven in, not continuous, discrete, ticking in tiny steps. No smooth flow, just fundamental units of now. Loop quantum gravity solves problems. It avoids the infinities of classical gravity. It explains the quantum structure of spacetime. Black holes are quantized too. Event horizons are made of these loops. Entropy emerges naturally. The math is elegant. Spin networks describe the loops. Spin foams describe their evolution. A dynamic, ever-changing structure. The universe is constantly reshaping itself. Nothing is fixed. Space and time emerge from relationships between loops. Matter interacts with these loops. Gravity is the geometry of this quantum network. Zoom out, and space-time looks smooth. Einstein's relativity emerges. The familiar rules apply. Zoom in, and you see the granularity. Reality is discrete at its core. This also gives hope for the early universe. Before the Big Bang, classical physics breaks down. Quantum loops could describe a pre-Big Bang state, a universe emerging from a quantum bounce. No singularity, no infinities, just fundamental quanta of space and time. Loop quantum gravity is testable, in principle. Tiny deviations in gravitational waves. Signatures in the cosmic microwave background. Hints of space-time discreteness might be detectable. It's a bold vision, radical, but grounded in mathematics. It tells us space and time are not smooth, absolute backgrounds. They are emergent, woven, and granular. This challenges our intuition. We think of space as a stage, time as a flowing river. But in this picture, both are made of countless microscopic threads, dynamic, interactive, and interconnected. Loop quantum gravity doesn't answer everything. It doesn't yet fully unify with matter, but it provides a clear framework, a way to merge relativity with quantum mechanics. one thread at a time. We are seeing space-time as something alive, something built, something emergent. The universe is a tapestry. Each thread contributes to the cosmic story. And through this, our understanding of space and time reaches a new depth. Space and time might not be fundamental. They could emerge from deeper structures. Enter AD-S divided by CFT correspondence, a breakthrough in theoretical physics. Juan Maldacena proposed it in 1997. He connected two seemingly unrelated worlds. On one side, a universe with gravity, anti-de Sitter space, curved space-time. On the other side, a quantum field theory without gravity, defined on the boundary. Here's the astonishing part. Everything happening in the bulk space-time can be described by physics on the boundary. No gravity needed there. Space-time geometry emerges from quantum information. Think of it like a hologram, a 3D world projected from a 2D surface. The bulk space-time is like the holographic image. The boundary theory encodes all information. Gravity, curvature, distance, everything emerges. Not fundamental, derived from relationships between quantum bits of information, from entanglement patterns across the boundary. This bridges quantum mechanics and gravity, hints at a theory of everything, shows that space-time can arise from more basic principles. A quantum scaffolding underneath reality. It also provides clues about black holes. The information paradox suddenly makes sense. Quantum information on the boundary preserves everything. Nothing truly disappears. Space-time and gravity in the bulk reflect the quantum rules on the edge. AD-S, divided by CFT, reshapes how we view the universe. Space is not a stage. Time is not a river. They are emergent phenomena. They arise from entanglement, correlations, and quantum structure. This concept aligns with Leibniz's old idea: space and time are defined by relationships, not absolute, not independent. Everything is relational. It's mind-bending. We are surrounded by a universe that seems smooth. Yet beneath it, a web of quantum interactions weaves space and time. Reality is coded in patterns, not in points in space. AD-S, divided by CFT, is still a work in progress. Many questions remain unanswered. Can we test it experimentally? Can it fully explain our universe? Physicists are exploring, slowly peeling back layers. One thing is clear: space-time may not exist independently. It emerges from quantum bits, from information, from relationships. The universe is a quantum construct. Our perception of space and time is an emergent illusion. Understanding this could unify gravity and quantum mechanics. AD-S divided by CFT is a hint at the deeper truth. We are learning to see the universe not as a backdrop, but as a tapestry woven from the threads of quantum reality. What is space? What is time? Are they real, or just our way of organizing experiences? Newton said, yes, space and time exist independently. Absolute, fixed, a stage on which reality unfolds. Leibniz disagreed. Without matter, space has no meaning. Without events, time has no meaning. Space and time are relationships, connections between things. Einstein complicated the picture. Space-time bends. It reacts to mass and energy. It's dynamic, not static. Quantum mechanics complicates it further. Space-time may be granular, made of tiny chunks. Perhaps it only emerges at large scales. AD-S divided by CFT suggests something profound. Space-time could arise from quantum information, from correlations, not from substance. We perceive continuity, but at a fundamental level, it's all relationships. Philosophers and physicists ask, if space and time are emergent, are they real? Does reality exist without them? Or do they only appear real because of the way matter and information interact? Consider this: we never perceive space directly. We perceive distances between objects. We never perceive time directly. We perceive changes, sequences, causality. Maybe reality is just interactions, events and relationships. We infer space and time from the web of interactions. They are tools, not fundamental substances. This view has radical implications. Causality may itself be emergent. The flow of time could be a macroscopic illusion. Our experience of now may not exist at the smallest scales. Yet for all practical purposes, space and time feel real. We navigate them, we age through them, we build civilizations within their framework. Even if emergent, they shape our lives. Philosophically, this opens questions about identity and existence. If space-time is relational, what anchors you? Are we just knots in a cosmic network? Do our experiences exist because space-time emerges? Or is space-time emerging because of our interactions? Some argue this view aligns with ancient ideas. Eastern philosophies and relational metaphysics suggest reality is made of connections, not objects. Modern physics may be circling back to these intuitions. Ultimately, space and time challenge our assumptions. They are not as simple as Newton thought. They are not fixed, universal absolutes. They may be emergent, relational, and defined by interactions. The philosophical takeaway? Reality is stranger than it seems. What we call space and time may be illusions of a deeper, relational order. Understanding this changes how we see the universe and ourselves. We started with a simple question. What are space and time? Newton gave us certainty, absolute, unchanging, universal. We moved along a fixed stage. Einstein shattered that certainty. Space bends. Time flows differently depending on mass and motion. The universe was no longer simple. Quantum mechanics added more puzzles. Space-time may be granular, made of fundamental pieces. At tiny scales, smooth space and time may not exist. String theory, M theory, and AD, divided by CFT, whisper another possibility. Space and time emerge from relationships, from information, correlations, and quantum interactions. Not fundamental, not real in the way we thought. Think about that. Everything we perceive, length, duration, distance, could be emergent. Space-time is a convenient illusion, a way for macroscopic beings to navigate a complex quantum world. What does this mean for us? It's unsettling. Our lives unfold in a stage that may not truly exist. Our clocks, calendars, and histories may all be emergent patterns. Yet, it also opens wonder. Reality is richer than we imagined. There may be layers beyond our perception. Beneath space and time, something deeper binds the universe. We can't feel the expansion of space. We don't sense the Planck-scale grains of space-time. But our tools reveal the hidden structures. Mathematics gives us glimpses into the underlying order. This is the frontier of physics. Questions no one has fully answered, perhaps forever unanswerable. But that's the beauty of it. Science is not about certainty. It's about exploring the unknown, challenging assumptions, pushing boundaries. If space-time is emergent, reality is relational. Everything is connected. The universe is a web of interactions. We experience space and time because of our place in that web. It's humbling. It's inspiring. It forces us to rethink existence itself. Maybe the ultimate truth is this. Space and time don't exist as we know them. They are shadows of a deeper reality. Our perceptions are limited. Our understanding is incomplete. And yet, we search. We calculate, observe, and theorize. We bend space-time in thought experiments. We chase the mysteries to the edge of black holes, across the cosmos, and into the quantum world. The journey is ongoing, and it is thrilling. So, as we end this exploration, ask yourself, what is real? What is emergent? What is waiting for us beyond perception? Subscribe if you want to keep chasing these questions. Because the universe is stranger than it seems, and we've only just begun to understand.